Hello, this is my Physics Lab 4 lab report. In the introduction, for the purpose of our lab, the purpose of this lab was to compare the predicted motion of a spring mass system to observe motion in the same system. We analyzed these two motions through comparing the different types of energy present in the system, i.e. change in kinetic energy, change in gravitational potential energy, change in spring potential energy, and the change in total energy of the system. For the assumptions to make this lab happen, I had the same calibration length, time between video frames, and physical characteristics of the system that was mentioned in the pre-lecture video. For the fundamental principles that we'll be using during this lab, the fundamental physics principles we use in this lab are Newton's second law, or the momentum principle, and the energy principle, in which we use these principles to observe the interactions between the system and its surroundings. The formulas we use in the experiment are Newton's second law, velocity update formula, position update formula, spring force, kinetic energy, and the gravitational potential energy formula. For the preview of the results, the predicted motion and observed motion are similar in both the x and y axes. Change in total energy is 0 because we decided that the system was the mass, spring, and earth. And since there are no surroundings, it means that there is no work being done on the system by the surroundings. For our initial conditions, we set the weight of the system to be 0.402. The initial position of the spring mass system was negative 0.125, negative 0.655. And then we also have gravitational constant, the spring constant, 6.88, which we got from calculating it using the formula k equals 4 pi squared times m over t squared. And our relaxed length of the spring is 0.127, which we got from the equation mg is equal to k L minus L naught. And for the equation of L, we got ball position minus spring position. And for L hat, we just took the magnitude, taking L divided by the magnitude. And for S, we took the magnitude minus L naught. And for our kinetic energy, we have 0.5 times the mass of the ball times the magnitude of the velocity of the ball squared. For the potential energy of gravity, mass of the ball times gravity times the position of the ball in the y-axis. And the spring potential energy is 0.5 times the spring constant times s squared. And we also have total energy, which is just all the energies added up together. For our actual code, we have our gravity, which is defined as the negative of the mass times the ball's mass times gravity. For the spring force, we have negative spring constant times s times L hat. For F net, we have just these two forces added together, which is F grav plus F spring. For our velocity, we just use the momentum principle, or the velocity update formula. And for our ball's position, we use the position update formula. For updating the spring, it was just the same code as before. And for our energy changes, we have k is equal to 1/2 mv squared of the ball. And for delta k, it's just final k minus initial k. For potential energy of gravity, it's just mass times gravity times h, which is the y position of the ball. And for delta potential energy of gravity, it's just ug minus ugi, which is potential energy final minus potential energy initial. And then we have the spring potential energy, which is 0.5 times spring constant times s squared. And then the delta us is just the final minus the initial. And the energy is the same as before, adding up all the energies together. And the delta E is just E final minus E initial. For our results and possible sources of error, as you can see, the x position versus the time graph shows that our model is accurate in its prediction of the x position of the mass, while the y position versus time graph shows that our model is a little bit less accurate in its prediction of the y position of the graph. Some possible sources of error are that some sources of error that may have occurred are that when making the data points in tracker, the center of mass might not have been consistently marked throughout the analysis. Another source of error may have been the lack of energies accounted for, as drag and thermal energy were both not accounted for, which could have changed our observations as well. For our what does it mean? Yes, the energy principle is satisfied. As time goes to infinity, the delta E value line remains at 0. This is the case because our system only consisted of the spring, mass, and earth, leaving no surroundings to do work on the system. So our total energy should be 0. And what if I calculated my oscillation period for the x position time graph to be 1.611 seconds, the oscillation period for the y 1.425, and the difference was 0.186 seconds. And as you can see, there's a slight difference in the oscillation periods when calculating periods using the exposition data and the y-position data. And these slight differences can affect our calculation for the spring constant, as using these two different oscillation periods would yield different k values. And in turn, this would also affect our spring force and spring potential energy calculations. This difference in oscillation periods can be attributed to the source of errors mentioned earlier. And that's it.